So we think that video games are amazing tools of cognitive enhancement because they selectively activate brain networks unlike anything we've ever achieved with any other intervention that's not experience-based, like drugs or devices. But that's just the beginning, that we can then use neural data to heighten those effects. Now, in order to do that, we had to build a new technology. This is known as the glass brain. It was developed by our lab in collaboration with a group at UCSD and a company called NVIDIA. And what you're looking at here is a combination of MRI and real-time EEG. And real-time, I mean, is that we do many algorithms, source localization, artifact correction, Granger causality, all of these processing within 0.2 of a second to get a look at what's happening inside someone's brain while they're engaged in one of our video games. And what you're looking at here is this MRI and EEG data from one person in our lab. Pretty much all of us have one of these glass brains in our lab now. And we're flying through the brain using a joystick. It's not really a movie, it's just a recording of us just navigating through a brain functioning in real time. I want to show you this example. So this is Mickey Hart, right? So here's the drummer of the Grateful Dead. We don't have a clinical example, so I think this is a fun way to show you one. So Mickey here is inside a virtual reality, the Oculus Rift. He has an EEG headset on, a wireless EEG headset. He's playing a game that we built for him called Neurodrummer. You can't see his game because it's just too big, but it's over here. So this is a demo after a keynote I did for around 3,000 people in California. And so Mickey's game is over here. He can't see anything. Sitting next to him, or anything in the audience, sitting next to him is Tim Mullins, who's on our engineering team from UCSD, and he's also wearing an Oculus Rift, but he's not looking at Mickey's game. He's flying through Mickey's brain, which you're seeing here, in real time. So I like to think of this as like neuro-Russian nested dolls, right? So you have Mickey in virtual reality playing a game, and Tim inside Mickey's virtual brain. And you can imagine a future scenario that a therapist like Tim is sitting here with their patient, and while their patient is playing a game, they're progressively challenging them with some virtual dashboard and then flying through their brain, looking at how those responses are changing. Why doesn't everyone change the same? That individual variability. And sometimes it's completely ignored. We love it. I love it. I love understanding why people are experiencing things that other people are not. And we don't really know. We are starting to dissect different factors in people's lives that seem to be predictive of their ability to improve. And I would say for something as complex as the human brain, we might never find a single solution. We have to think what we call multimodal, working across many different types of interventions. And perhaps the biggest deficit is that these are open loop systems. An open loop system is one that has a very long time frame between how you intervene and how you adjust that intervention. We like the idea of not just playing games with your fingers, but moving your entire body. And I'm going to give you an example of that from a game that we developed. Just a couple words about this. We call this ACE, and the idea behind ACE was to develop cognitive assessments that use those same closed loops, but not to improve your brain, just to sample how your brain is functioning very rapidly. We don't have to get rid of meds. They do valuable things, but maybe at 1/10 of the dose with much less side effects. And then you use a game like ACE to figure out how someone is actually functioning. We have another version of ACE called NeuroACE, where we're going to do EEG in the classroom and at home to understand how all these cognitive functions are occurring in the brain. We can also take EEG data and feed it into one of these, which is known as a neurostimulation device, in this case, TACS. This is a transcranial alternating current stimulation. And that's a fancy way of saying that with a very low voltage electrical field, we can pulse in frequencies electrical currents into the brain. You can't even feel it. But what we're doing is we can take the brain data, let's say theta from the experiment that I showed you earlier, stimulate the brain at theta, just at those key parts in the game, and give a boost to the plasticity. You can imagine someone with a traumatic brain injury where they're playing this customized game using EEG to guide the gameplay and then use a stimulator so that they can have increased plasticity in those areas that you're trying to improve. And so what we wind up with here is something that is targeted to the neural systems. It's personalized, and not even just personalized, it changes with the person over time. It's multimodal, right? Many different systems working together, many different games, including the potential to keep pharmaceuticals on board at a lower level, and then multiple closed loops acting together. And what's perhaps the most powerful part of this is because the technology we're using is already in the consumer space, we're looking at real world and real time. Something that has been a real challenge for physicians, right? We see a patient in these rare snapshots and then we don't see them again. Here, we can constantly be monitoring and trying to improve them over time.